For lesson 4, we're going to look at present value of an ordinary annuity. So we've been talking about compound interest first, which is where you would deposit a lump sum of money and then figure out with interest how much you might have several years later. Then we looked at present value with regards to compound interest, and we were wondering, in order to have $10,000, how, like in 4 years, how much should I invest today? So we looked at this formula here before for just present value. Then we looked at what an ordinary annuity was. So lesson 3, we were looking at making regular deposits into an account that is earning interest, and then how much would you have later on if you paid at the end of every month or at the end of every year. Those regular payments are what make it an annuity. So now we're going to look at present value of an ordinary annuity. So again, looking at, for example, imagine depositing or having $50,000 today, and then you're going to make regular withdrawals from that amount. So you're not, that's what makes it present value of an ordinary annuity. So it says an annuity can be purchased to provide a number of equal payments for a specified period of time. A lot of people might do that, make a large lump sum investment, but then take out regular payments. So we're going to use this original formula that we had for present value in order to look at example 1. So this is a pretty typical example. Krista wants to deposit enough money today so that she's going to put it in an account. The account is going to earn 8% per annum, so 8% per year compounded annually. Then she wants to make regular withdrawals of $3,000 at the end of each of the next 3 years. So at the end of each year, she wants to take out $3,000. So most people would say, well, she just has to put in $9,000 and she'd have enough money. But the idea is she's actually going to make interest on the money that she deposits today. And it doesn't have a long time to gain interest and in order to make $3,000 in the first year, but she'd have 2 years for her investment to make some interest to come up with $3,000 in the second year, and then she'd have a full 3 years to wait in order for that interest to accumulate to get to that $3,000 after 3 years. So if we look at this and break it down with the formula that we already know, just for our first example. This one here, for 1 year, the present value of $3,000 at 8%, so just using the formula we saw in the last lesson, this would be 1.08, so it's 1 plus the interest to the exponent n, which is how many years you have. And that's 2,777.78. So what that is saying is, if she wanted to have $3,000 at the end of 1 year, she'd only have to deposit 2,777, because after a year, the extra interest she's making, it would bring it up to $3,000. So we have to do these each separately if we use this formula, which obviously is not going to be our main way of doing this. The second year, it's 1 plus the interest to the number of years or the number of compounding periods. This is just annually, so that's why I didn't have to do many calculations there. She would only have to invest $2,572.02, and because that amount of money would sit there for 2 years at 8%, and she'd end up with $3,000 when she was done. For the third year, we would have the $3,000, 8%, 0.8, and then the exponent is 3. So since it's sitting there longer, today she would only have to invest $2,381.50 because it's going to sit there for 3 years, and at the end of 3 years at 8%, she'd actually have her $3,000. So if we add those up, we'd have $7,731.30. So therefore, that's what Krista must deposit today. We are going to use a formula that makes this a lot easier to do. Present value, R stands for the regular payment amount. And then it's just a little bit rearranged here. It's 1 minus 1 plus I to the exponent negative n divided by I. So it's going to be just sort of tricky to type into your calculator, but this is the present value of an ordinary annuity. We are going to really like it if the payment period is the same as the compounding period. It doesn't necessarily have to be, but we're going to look at mortgages next, and I'm going to show you a quick fix if they aren't the same. But what we like, what makes this easier, is if paid every 3 months. Every 3 months is quarterly, and this is going to be compounded quarterly. So we like those to match. It makes the formula, using the formula, quite a bit easier. So what we have here, example 2, a debt is to be paid in installments of $250 each, paid every 3 months for 3 years. So 4 times a year, and then for 3 years. If the first installment is due in 3 months, and the interest being charged is 20% per annum compounded quarterly, determine the present value of the debt. So that's kind of helpful when it says, what's the present value of the debt? How much do they actually owe? So what we have, they are, is the payment amount. So it says that they're going to make payments of $250. The present value is what we don't know. How much is the loan actually for? How much do they owe right now? The interest rate is really high, 20%, but it's quarterly. So that's 0.05. And then the number of compounding periods, 3 years, but 4 times a year. So that's 12. So we have this big formula. It's really not too bad. Present value equals the regular payment, 1 minus 1 plus I to the negative n divided by the interest rate. So we just sub everything in. So 250, 1 minus 1 plus 0.05 to the negative 12 divided by the 0.05. Okay. So again, I'm a BEDMAS person. I would type, this is exactly how I would punch this in to get the right answer. 1 plus 0.05 equals to the exponent negative 12. So you can do your exponent or whatever your button looks like on your calculator. But your exponent's going to have to be negative 12, a negative number. So not the minus button, but the negative button to the exponent negative 12. Find out what that is, equals, and then go 1 minus your answer. Some of you might not notice, but I could write down this big decimal here, but 1 minus your last answer. Check your calculator to see if it has an answer button, because man, they're really, really fantastic. You can push 1 minus whatever my last answer was, and it'll pull that last answer up so that you don't have to type it in. It's really, really nice. So if I type all of this in and get an answer, then I go 1 minus answer. It'll do that for you without having to write it down. It's just easier. And then I'd say, okay, equals, and then times 250, and then divide that by 0.05. So one thing I could show you is that on the right side, I get 0.44316,258. And you know that I'm using lots of decimals because I'm trying to get a really close answer that's, they can be amazing. They can be really off if you round too much. Like you'll have something very different than me if you didn't use a lot of decimal places. This is more accurate, obviously. So the present value, what they actually owe today is $2,215.81. Because they're going to pay $250 4 times a year, but there's also interest being charged on that. Okay, last example, just something to show you as well. Dan won $25,000 in a lottery. That's today. Okay, he won money, let's say today. The winnings will be paid in equal monthly installments for the next 4 years, starting 1 month from now. So the money earns 7.5% compounded monthly, and he's going to get monthly payments. So if those match, it's a lot easier. Determine the monthly installment. So this time, our regular payment, we don't actually know what that is this time. The present value, though, is $25,000. That's what he actually just won. The I, same thing, 0.075, but divided by 12 because it's monthly, 0.00625. And the N is 4 years, 12 times a year, so 48. Okay, so same formula, but I think you might notice this is a little different. It's talking about present value, so I have to use the present value formula. It's saying that he won this already. It's not that he's going to win $25,000 in 4 years. He won it today. So it's a little bit backwards though, because I know the present value already. I can use the same formula, but I'm going to sub in the present value on the left that I already know, and the R is what I don't know. So you can use the same formula and work backwards. 0.00625 to the negative 48. I'm going to be able to work backwards and solve for the R. Okay, so again, I really like to just imagine multiplying both sides by 0.00625 because it would cancel out on the right. And over here, I kind of do this when you see my notes. I just kind of multiply this side by 0.00625 and I get 156.25. Then I don't have a fraction anymore. And then this part here, I could figure this out maybe. 1 plus 0.00625 equals to the exponent negative 48. And you could then do 1 minus your answer because you wouldn't have to write all this down because I'm kind of writing it down just to explain, but you don't have to write down everything. Now that I have that, again, I probably would just type 1 minus this equals, and then 156.25 divided by answer, divided by my last answer. It just saves you a lot of time. And so you don't have to write all of these decimals out. Plus, when you hit answer, it takes that really long, the answer that you had with all of the decimal places included. So it really does give you a more accurate answer. So 0.258489819. And then to get R by itself, I just want to divide both sides by that decimal. And I get a regular payment of $604.47. So the monthly installment is $604.47.